In this lecture, we are going to focus just on London dispersion forces. Um, so these are the weakest of our intermolecular attractions to other molecules. Um, and this is because they have the smallest amount of constant charge that is being attracted between opposite charges. And so what dispersion forces arise from is temporary and spontaneous changes in the electron density on a particle to interact with other ones. And so they create these temporary dipole moments. So I've got pictures here on the screen of carbon or methane. So it's carbon and 4 hydrogen bonds. And so these would be, in this example, nonpolar. So I would have two non-polar particles. I'd be like, well, the charge distribution is even. And so when we bring them together, they're just these two balls of negative energy. They should repel each other, right? But they don't. They are attracted to each other. And and remember, it's not just a ball of negative energy. There's that big positive charge from the nucleus smack in the middle. And so what happens as you bring these together is that the electrons on the outside of one of those methane molecules are actually becoming attracted to the nucleus on the other particle, and a little bit. They're pretty far apart, right? And so as they come together, the electrons in the particles shift around. The electron density is such that it creates a little shift that says the electrons are a little bit more likely to be found away from that other molecule. And that would create a temporary dipole moment, right? Where we have partial negative charge on one side and partial positive charge on the other. And once that happens, that affects the one coming in close to it. And it then has partial, it'll shift its electron density around too. So that way the electrons are a little bit more likely to be found on the side of the molecule that is interacting with the other molecule's partially positive side. And that'll create a partially positive side on the other side. And so it's just kind of this little blip, right? This little moment where the electrons are just like, oh, it's a little bit more likely that they're over here and here, and create this partial dipole moment. So less than a plus or minus one charge, significantly less. And that creates this little attraction. But now we're talking about particles that are going to be surrounded by lots of particles. So that temporary attraction happens to one and then the others, and then it starts happening simultaneously. And the way I kind of think about this is kind of shown in this picture right here, that it really creates basically static, right? Like it's like if you imagine static just kind of shifting around based on its environment, and if it's constantly changing in the liquid state, then that's just constantly changing. Now, if it's in the solid state, then those positions of those particles are more permanent. And so, or not permanent, but stable. And so that temporary dipole moment doesn't change quite as much possibly. And so that's what London dispersion forces are. And that means that everything with an electron cloud will experience the intermolecular force of London dispersion forces. Everything. Now, my challenge to you is this: what wouldn't have London dispersion forces? Like, can you think of something that would fit the bill? I'll leave that hanging. Um, so everything has them. But within everything having them, some have stronger London dispersion forces and some molecules have weaker London dispersion forces within the relative weakness of the force itself. And so what dictates how strong those London dispersion forces are is the polarizability and the surface area of the molecule. And so we see that as polarizability, and that is going to be how easy it is for electrons to move and shift and change. And then also surface area, which is really just the size of the molecule. So again, that polarizability is that ease with which electron clouds can be distorted. And we see that is the electron cloud is easier to kind of distort with larger atoms and molecules. Because in a larger atom, the valence electrons, the ones that we care about shifting around because they're interacting with other particles, those are going to be a further distance from the nucleus. And so they will have less of a attractive force between themselves, the electrons and the nucleus, which allows them to kind of have a little bit more freedom. And so they're more polarizable, or he'd say they're just easier to make a temporary dipole moment out of. We also see that things that have like a low net effective charge or Z effective would also be more polarizable. Anything with a really large electron cloud would be more polarizable. And so we see that large molecules that in general will have stronger London dispersion forces for this reason. Now, the other reason though is size. It's that surface area component. As there's more surface area in a molecule, the larger it is, the more atoms it's made up of, and the less compact the structure of the molecule is, then the more surface area it has, and the more points of contact that molecule can have with different molecules around it. So the more molecules it can interact with, the more of these temporary dipole moment attractions we can create. And so we see greater London dispersion forces impacting their physical properties. So it's both. And you kind of have to weigh and balance them, right? Like the polarizability and the surface area when you're comparing two molecules. And so here we can show an example of where we'd have a large area right here versus a smaller area for two molecules that are the same size. And so having the chain of carbons rather than a branching carbon structure would create a larger surface area for that molecule to interact with more things. All right, let's look at an example here. So I've got two separate examples. They're kind of lost here. I'll put a little line. So first, let's compare fluorine and iodine and decide which one is more polarizable. So on the periodic table, well, bad periodic table. Fluorine is up here on the top right-hand corner, and iodine is down on the bottom. And we know from our periodic trends that size increases as you go down the periodic table. So my iodine is just a larger molecule, and my fluorine is a smaller molecule. That smaller means that the electrons on the fluorine that are in the valence shell are much closer to the nucleus. Now, they both have similar effective nuclear charges of +7, but again, that iodine is a larger molecule, so there's more shells of core electrons between the nucleus and the valence electron, so it has a larger radius, but it just means those electrons are more polarizable. They're easier to move around. And so our iodine will be more polarizable. And so I would expect it to have larger London dispersion forces. And London dispersion forces is a lot to write. I typically abbreviate it LD. So let's look at the next one. I have C6H14 and C3H8. So these are carbon and hydrogen atoms that form both of these molecules. So those are the same. Like the polarizability of a carbon versus a hydrogen would be the same. But when we look at the two overall structures, we can see that our C6H14, our hexane, is just larger, and our C3H8 is smaller. And they're both just chains, but the C6H14 has more surface area. Therefore, we expect it to have stronger London dispersion forces.